students, I hope all of you are following the online classes, and then you are preparing the notes, and I hope you are solving the problems from that worksheet. In the previous classes, we discussed some Coulomb's law applications, that means the numerical problems based on the Coulomb's law, and now we are going to discuss some other models based on the same Coulomb's law application. And so in that especially there are just actually if you know the Coulomb's law basic formula and other concepts which we discussed in previous classes, that means in the 11th class, with the help of this Coulomb's law formula and the previous knowledge you can solve the remaining problems based on this Coulomb's law actually. So just I am going to discuss some other models, how the Coulomb's law can be linked with this mechanics or how it can be linked with this other topics. And so here first let us consider one of the problem here related to this mechanics, combination of mechanics and this Coulomb's law. And let us consider this two identical blocks are placed on this smooth horizontal surface. Write it as a problem. So two identical blocks, each of mass 2 kg, are placed on a horizontal surface at a separation of say 1.5 meters, and they carry the identical charge. That identical charge 50 microcoulombs each. Now the question is, when the blocks are ready to move, that means when the blocks are tending to move, we need to find the frictional coefficient of friction between the blocks and the surface. We need to find here by assuming that coefficient of friction is same for both of them. So that the mu value we need to find. And so for that, this is the given data. The mass of each block is given as 2 kg and the charge on this each block is 50 microcoulombs. And so for that, now the system is in equilibrium, but just it is ready to move now. And so now for this, just I am taking the FBD of this block A. When you are taking the FBD of this block A, the forces acting on this mg is acting in downward direction, normal reaction from the surface upward direction, and this repulsive force, electrostatic repulsive force on this block A will be towards left. And now this frictional force will be towards right to opposite this force. And now just balance, the body is ready to move, and so that means it is almost in equilibrium now. And so now we can write this N is equal to Mg and F is equal to Fl. This limiting friction. As the body is ready to move, that means maximum frictional force act on that, so that we are taking that as limiting friction now. And just I am substituting the repulsive Coulomb's law formula here. So that is K value, constant value 9 into 10 power 9. As both the charges are same, Q square by R square. That is equal to, as it is limiting friction, you can write mu L. Now we need to find this mu value here. So that mu value is nothing but, you can substitute these numericals here. I am writing this mg value. That mg is nothing but 2 into 10. The g value I am taking it as 10. So you can simplify this. So it is 9 into 10 power 9. So it is 5 into 10 power minus 5. So it is 25 into 10 power minus 10. And this 4 will comes to the numerator. Why this is 9 into 20. So I can simplify this as this 9 you can cancel here, and this 4, 5. This 5 you can cancel 5. So we'll get 0.5. So now this will be the coefficient of friction or coefficient of static friction between those two surfaces, between the block and this horizontal surface. So that is the way of solving that. Just in addition to the already previous known forces, now additionally this Coulomb force will be there. So that Coulomb force, whether it is towards right or towards left, depending on the charges we need to consider. And additionally we need to include that Coulomb force here. That is only the difference. It is like our previous mechanics problems only. And next similarly let us see another problem based on this Coulomb's law and the combination of this mechanics. So let us consider a charge Q is fixed here. So here a charge Q is fixed, capital Q is fixed charge here. And now a small q is this is small q, and mass of this particle is m. Now this charged particle is free to move, and the surface is total surface is the smooth surface. So initially it is at a distance of say r or x1. So I am taking this distance as r. We need to find the speed of the particle when this distance is x. That means when it moves to this position, we need to find the speed of that particle. That means, so again note that problem. A small point charge of charge q and a mass m is released from a distance r on a smooth from a distance r from a fixed charge q on a smooth horizontal surface. Then find the speed of the charged particle when it reaches a distance x from the fixed charge. So that means when it reaches to this position, we need to find the speed of that particle. When you are releasing from rest, the initial velocity of this particle is 0. So the initial velocity of this particle is 0. So we need to find the final velocity of this particle when it reaches to this position. And just you can apply this actually conservation of, that means if in electrostatics also we know that potential energy, electrostatic potential energy will be there. So we will discuss it later. So as we don't know about the electrostatic potential energy as of now, so you can't apply the conservation of energy. If it is completed, you can apply the conservation of energy directly here. And so now without applying conservation of energy, now we have to solve this problem. And so for that, you can simply consider the force acting on it when it is at a distance, some intermediate distance here. I am taking that intermediate distance as some a, or let it be, generally we are taking it as x, so we can finally take that limit as x. So intermediate distance, when it is here, I am writing the force acting on this. There will be some force acting on this particle, which is F, repulsive force. And so that repulsive force we can write it as K into capital Q into small q by x square. And this force we can write as ma, where a is the acceleration of this particle, so which is K into q by x square. And therefore this acceleration of the particle we can write as K into q by m into x square. This acceleration of the particle. And now this acceleration of the particle, from this you can observe this acceleration of the particle is a variable. That means it is a function of x. So as the distance is changing, you know the force changes, and so automatically acceleration changes. So as the acceleration is not constant, so we can't use the kinematic equations. So just we should use the calculus to calculate, that means integration, to calculate the speed of the particle. And so we know that that acceleration a can be written as v into, in terms of x, we can write it as v into dv by dx. We can write, generally we define it as dv by dt. In terms of displacement, we can also write like that. Therefore, I can write this as v into dv by dx is equal to k into capital Q into small q by mx square. So just by rearranging the terms, integrate this. K into capital Q into small q by m into, this is dx by x square. I am taking integration on both sides. So initially it is starting from rest, we need to find the final velocity, and this is from initial separation is r and final separation is x. So finally the separation is x itself. And so now we can differentiate this, integrate this here. So you can get this value as vf square by 2 minus 0, the lower limit, and this is kq by m. Here x square integration, you know the integration formula, 1 by x square integration. So you get like minus 1 by x, and limits are from r to x, and therefore this vf square by 2 is equal to kqq by m into, here if I substitute these limits, 1 by r minus 1 by x you will get because of the negative sign. So finally you can write this expression here, and I am substituting this k value also, which is nothing but 1 by 4 by epsilon naught. Then this 2 you can cancel in that. So finally I can write this as qq by 2 pi epsilon naught into m into 1 by r minus 1 by x, this whole power 1 by 2 or under root. So that is the velocity of the particle when it is at a distance x from s. So like that, Well, already we know the principles of this mechanics, and so just we need to include that Coulomb force whenever such interlinked problem is given. So just we are writing this acceleration equation. As the acceleration is variable here, so we are getting this. We need to integrate this equation. We can't apply the kinematic equation. Just this mathematical calculation. Just we are doing the integration here to calculate the final velocity of the particle when it is at a distance x from it. If conservation of energy is completed for you, that means if electrostatic potential energy is also completed for you, you can solve easily by applying that conservation of energy. Then easily you can do that without using that integration. So after that completion of electrostatic potential energy, you can do the by that method. So until now we are discussing actually about the applications of Coulomb's law in terms of the point charges, or we are calculating the Coulomb force between the 2 point charges. And now let us see how to apply this Coulomb's law in case of continuous charge distribution. So that continuous charge distribution may be of different types. That means in continuous charge distribution, types of charge distribution. So there can be 3 types of charge distributions here. So one is linear charge distribution, which we define it as linear charge density here. Let us see the definition of linear charge density. So linear charge density is nothing but we define the linear charge density when the charge is distributing on one-dimensional object, like a wire. If you are taking a wire and if the charge is distributing on this wire, then such a distribution is nothing but we call linear charge density. Linear charge distribution. And so in that linear density we can define it as the linear charge density we can define it as charge per unit length. That means charge by length we need to write here. So which is nothing but Q by L. And from this you can easily write the unit here. So it is Coulomb per meter. So that is the meaning of linear charge density. Total charge per total length. The ratio is nothing but we call linear charge density. And this will be generally we use the linear charge density for the one-dimensional object like a ring or a wire when it is distributed on a straight wire. We need to use this linear charge density here. So that is our linear charge distribution. And the next one is aerial charge distribution. That means we call aerial charge density, or that is also called surface charge density. Surface charge density. So that surface charge density is generally represented with this sigma. That means when the charge is distributing on a plane surfaces, when the charge is distributing on a disc, or when it is distributing on a metal plate like a square plate or rectangular plate, then such a distribution is called aerial charge distribution or surface charge distribution. And correspondingly we define the density here that we call surface charge density. And so surface charge density is represented with this sigma, and which is defined as charge per area, charge per unit area. And therefore you can write this as Q by A. And so you can write this as Coulomb per meter square. So that will be the unit for this surface charge density. And the next type is for the 3-dimensional objects. So volume charge density, or simply you can define it as charge density. You can call it as volume charge density or simply charge density, because generally the density means you define in terms of the volume. And so now here in this case, if the charge is distributing on a 3-dimensional objects, like if it is distributing on a sphere or a shell, or if it is distributing on a cube, then it is that means inside the cube throughout the volume of these materials. And so then when it is distributing on a sphere, solid sphere inside the sphere, and inside the cube, that means throughout this volume, if the total volume it is distributing, then we call it as a three-dimensional charge distribution, or which is nothing but volume charge distribution. So then correspondingly we define the volume charge density. So then it is represented with this rho. So charge per unit volume. And so therefore I can write this as rho is equal to Q by volume we need to write. Volume in which the charge is distributed, and so this is Coulomb per meter cube. So these are the three types of charge densities we use here in continuous charge distribution problems. Linear charge density, that means charge per unit length, surface charge density, charge per unit area, and the charge density or volume charge density, which is charge per unit volume. So now let us see some problems based on this. So in case of linear charge densities problem, let us see the first problem here. Charge Q is distributed on this rod uniformly. This is a rod of length L. Now a point charge is placed here. A point charge small q is placed here, say at a distance of d from the center. D from the center of the rod. So now we need to find the force acting on this point charge due to the rod, or we may calculate the force acting on this rod due to this point charge, because we know that Coulomb force is an action and reaction pair. So force acting on any one of this object you can calculate here. So that means now it is a continuous charge distribution. In the Coulomb's law limitations we discussed that actually the Coulomb's law is valid only for the point charges. If you are taking the two point charges, then directly you can apply the Coulomb's law here. But now this is a point charge here. The another object is not the point charge. So it is some distribution is taken here. Charge distribution is taken. So when charge distribution is taken, so you can't apply the Coulomb's law directly, right? So then we can't apply the Coulomb's law directly means now we divide the object into small parts and then we do by integration method. That means we need to use the integration here. So for that I am taking a small element here. So let us take a small element of this object here at a distance of x from this. X from this point charge, and this is dx. This element is dx. And now the charge present on that small element. So first write down this problem. On a rod of length L, a charge Q is distributed uniformly. A point charge Q small q is placed at a distance of d from the center of the rod as shown in figure. Then find the force acting on the rod due to this point charge. So that is our question now. So now let us see here, to solve this, first we are taking the small element and now we need to find the force between this small element and this point charge. And we are taking the small element such that it is very small, such that it can be taken as a point charge. Because our point charge definition is nothing but when the size of this charge is negligible when compared to the distance between them, you can treat that as a point charge. So here we are taking very small element such that when compared to this x, this dx is very small. So that we can take that as a point charge. So that we can apply the Coulomb's law between that element and that point charge. So for that, first I am writing the charge present on this element here. Let it be dq. So charge on small element. So charge on this small element dq, we can write it as lambda into, where lambda is the linear charge density which is charge per unit length, lambda into the dx we need to write, length of that element. And so now let us define that lambda now. So you know that lambda is nothing but charge per total charge is q and it is distributing on a length of L. So q by L into dx. So this is our dq value. Let it be equation 1. Now let us write the Coulomb's law between those two elements. That means this element and the point charge. So for small element, I am applying the Coulomb's law. dF is equal to the constant I am taking it as k into dq into q by the separation between them is x square. That the separation between them is x, so you can write that as x square. Now let us substitute this dq value here. Therefore this df is equal to, I can write it as q by L into x into q by x square. So that finally I can write this as kq is dx, kq into q by L into dx by x square. And so to get the total force acting on this point charge or total force acting on the rod, now we need to integrate that. So the total force on this rod so that is F is equal to kq into q by L integral of dx by x square. So in this type of problems it is important to write the units, the limits for this integration. Sometimes they will give this d value from this end, or sometimes they will give the d value like this from the midpoint. And so now we need to write this Excel limits according to the given data. So in that, to write that limits, you need to read the question carefully, that whether they are giving from end or they are giving from the midpoint. And so now here the question is, it is given from the midpoint, so let us write the limits from this midpoint. The lower limit of x is here, that means this rod starts here at a distance of d minus this distance we need to write, which is nothing but L by 2. And so in this lower limit you can write as d minus L by 2. And the upper limit is nothing but this end. That end is nothing but d up to here it is d plus this L by 2. So d plus L by 2 we need to write here. That is the upper limit. And just integrate and simplify this, you will get the expression for this force acting on it. So minus 1 by x you will get, so I am substituting these limits, d minus L by 2 minus 1 by d plus L by 2. So this integration here, the integration of this 1 by x square is nothing but minus 1 by x. So after substituting the limits you will get like that. Now we can take LCM and simplify this. Like if I write this, the simplification kq by L into, you can take LCM now, this you will get like L by d square minus L square by 4, right? If I take the LCM here you will get d plus L by 2 and here it is minus d plus L by 2. So that the minus d and plus d will be cancelled, and so that you will get like this. And now we can cancel this L. So finally this is kq by d square minus L square by 4. So that will be the expression for this force between those two charges. And sometimes here instead of giving this q value, they may give this lambda value directly. So then accordingly we need to write here. So instead of this q by L directly we need to substitute this lambda. Or finally this q value you can write it as lambda into L. So like that also you can write here. So that is a way of calculating for this continuous standard distribution. So for the continuous standard distribution, first you need to take the small element like this, and then we need to apply the Coulomb's law between that small element and the point charge. And then we will get some expression like this. Then just after this, to find the total force we need to integrate that. So just by doing the integration with the proper limit, you can calculate this total force between those two objects. So let us see one more example here. So like this, a charge Q is distributed on a rod which is bent in the form of a semicircle. Now this another point charge Q is placed at the center. And so again we need to find the force of interaction between those two. And here let us consider this as I am taking this Q is the charge distributed uniformly on this. So let us take this Q is the charge distributed on this. And this is of radius R. The radius of the ring is semicircular ring is R. Now here I am placing another charge here. A point charge Q is placed at this point, at the center. Now we need to find the force of interaction between them. That means note down the problem. A charge capital Q is distributed on a semicircular ring of radius R uniformly. A point charge Q is placed at the center of the ring as shown in the figure. Now find the force of interaction between the ring and the point charge. So then that is the question. Now let us see how to solve this problem. So similar to our previous problem. So for any continuous distributed problems, so the procedure is first we need to take a small element and let us define the charge on the element first. That means the dq value. And after defining the charge on that element, so we can apply the Coulomb's law between those two elements. And then just integration by taking the proper limits. And so now here let us see here. In this problem, I am taking a small element like this. This is angle theta and this is the d theta. So this is our element now. This is the element where this charge dq is present here. And so now let us define the charge on that element now. So charge on small element. So that the dq value we can define it as. Now again this is one dimensional only. One dimension means it is a linear charge density only. So we need to write it as lambda into. Lambda is nothing but charge per unit length. So charge per unit length into length of that element we need to write. So let us see how to write here. The total charge is given as q by length of this element. Length of this element means it is a semicircle, so I can write its length as pi r. And into this is our lambda value, charge per unit length, into length of that element. Like in the previous problem we mentioned like dx. Now the dx value we need to write here. The dx means length of this arc we need to write here. So that length of that arc I can write it as r d theta. Because this angle I am taking it as d theta. And therefore this you can write it as q by pi into d theta. So this is our dq expression. So let it be equation 1. And next let us write the force between the force due to small element. Force due to small element. So that force due to small element I can write it as dF is equal to k into dq into q by r square, the distance between them, distance between that element and this point charge. The dq value you can substitute here. So I can write this as q into q by pi r square into d theta by substituting the dq value here, q by pi into d theta. So next here, in this type of problems, in the previous problem, after writing this force acting on this small element, we directly integrated. So whenever you are doing such a type of problems, whenever it is continuous charge distribution is there, actually it is not only in this topic, it is common for every topic. Whenever you are going to integrate a vector quantity, first we need to find direction of the vector. Whether the direction of this vector is same for all the elements or it is different for different elements. If it is same for all the elements, you can integrate directly this df value like our previous problem. So in the previous problem you can consider that you may take any element of the rod, the force on the point charge will be in the same direction only, right? But here let us see, if I am taking this small element here, then force acting on this element will be on this point charge will be along this direction, say this df. And next, whereas if I am taking symmetrical element means suppose I am taking this another element like this. I am taking the another element here. with this identical element. This is d theta. And so now force due to this element, this again I am taking this charge as dq. Now force due to this element will be along this direction. Right, same amount of force will be there because we are taking an identical element dq and dq, that means at the same angle theta and theta. And so now that force will be along this direction. And so now because this element is producing the force along this direction and this element is producing the force along this direction. So different elements are producing the charge in different directions, right? And so that you can't integrate this equation directly. So that means whenever you are integrating a vector quantity, you should verify this whether the vector quantity due to all the elements is in same direction or not. Not only in this problem, it is same for every problem. Whenever you are integrating, whenever you are doing such a problems, the procedure is same. So now here, when the different elements are producing that is exerting the force in different directions, either you can resolve this f into components and you can integrate, or you can take, if the body is symmetrical object like this, if the body is symmetrical object like this, you can take an identical element here. So if I am taking identical element here, now we are getting the force like this. So if I am resolving this into components, so if this angle is theta, I can say then this angle will be theta with the horizontal. So this angle is theta and similarly this angle will be theta. Now we can observe this. Its component along this direction will be df cos theta. And similarly its component along this direction will be df cos theta. And so now whereas this vertical component will be df sin theta will be along this direction. And due to both of them, if I consider 2df sin theta, so 2df sin theta will be in downward direction. And so now these two components are equal in magnitude, opposite in direction, so they cancel with each other. And so no need of calculating the along horizontal direction, that means along x direction. So only we need to find the force in this y direction, or you can conclude that the net force acting on this point charge will be only in downward direction, that means along negative y direction. There is no force acting along this x direction here. That is our conclusion. And so now directly I am integrating that. So net force on small q. So it will be like f is equal to integral of 2df sin theta. And here, as you know, in previous 11th class also we did many problems like this. When you are taking this 2 here, the factor 2 here, only we need to take half of this given object. That means only half of this given figure here. That means 1/4 of the circle only we need to consider. That means theta value we need to consider from 0 to 90 degrees only. If you are not taking this 2, then this theta value should be considered from 0 to this 180. We are taking 2 means this element we are considering and this element also we are considering. Like that, if you take this 1/4 of the circle, automatically this 1/4 of the circle is also considered if you are taking that 2. And so that we need to integrate this theta, we need to take the limits from 0 to 90 degrees only if you are taking that 2. If you are not taking this 2, only if you are integrating df sin theta, then theta value we should take for the total figure. That means from 0 to 180 degrees, complete semicircle we need to consider. In first year also such many problems are there. And so now let us integrate this. So integral of 2 df. df is nothing but we can substitute here k into capital Q into small q by pi r square d theta. This is our df value into sin theta. So as I said, limits we need to take from 0 to pi by 2 only, because we are taking the factor 2. And so now we can write this as f is equal to constants I am writing outside 2 k q capital Q into small q by this pi r square. This totally it is a constant value, pi r square into integral of sin theta and d theta. So only the sin theta is a variable here. So 0 to pi by 2. So we can do the integration here. Therefore this f is equal to 2k q by pi r square, and sin theta integration is minus cos theta, and limits are from 0 to pi by 2. And so if we substitute that limits, cos of minus pi by 2 you will get get, which is 0 cos 90, minus of minus plus you will get cos 0, that is 1. That means this total value will be 1. So I can write this as 2 kq by pi r square into this value will be 0. The first value is 0 plus 1 you will get. And so finally we can write this as kq by 2 pi square epsilon naught into r square. That means I am substituting the k value. K is 1 by 4 pi epsilon naught, and so this 2 will be cancelled with that 4. You will get remaining 2. And here already pi is there, so in this also you will get one more pi, so that pi square here. So then that is our force here. And if you want to express it in vector form, we can also mention its direction as minus j cap. Because that force is acting like this. That force will be along this negative y direction. So while answering about the direction, you need to cancel the distribution. So like suppose in the same problem, this is positive charge and if it is negative charge is given, then force will be attractive force. And so then you will get force direction will be along this j cap you will get. So that finally when you are answering the direction about that force, you need to observe that whether the force is attractive force or repulsive force, and from that we can answer that. So that is another example for this continuous charge distribution here. So just again we are taking the small elements. So first we are defining the charge on that small element, and then we are writing the expression for force due to the small element. So after writing this, you need to check whether the force due to elements are in same direction or different direction. If they are in same direction, then directly you can integrate this expression. If they are in different directions, you can resolve them into components and you can integrate like x component and y component separately. Or if the object is symmetrical object like this, you can cancel an identical element here, so that one component will be cancelled, then net force direction will be only in one direction. So only this component you can integrate here to find the net force on this cube. So it is a procedure to find the charge on this. Now here, if suppose we calculated only for this semicircle. Now suppose if complete circle is given and a charge q is present here. A complete circle is given and a charge q is placed at the center. If I ask what is the force acting on that point charge due to this complete circle. So that is nothing but simply you can answer it as due to this semicircle, we can apply this formula. If this is also positive charge, due to this semicircle, that force will be say F in downward direction. Due to this lower semicircle, again the force will be there, that is also repulsive force. Then same amount of force will be there along this direction, right? Just now we discussed now. Due to this semicircle, due to the upper semicircle, the force acting on this will be in downward direction. And due to this lower semicircle, the force acting on this will be in upward direction. And so that the net force acting on this will be 0. So the net force acting on this ring is 0. If the complete ring is given. But in the same question, when the complete ring is given and a point charge is placed at the center, that force will act on the ring also. Now there will be a question like because of that force on the ring, so then this ring will experience the force, every element of the ring will experience the force like this. It will experience some repulsive force in outward direction. And so that because of this repulsive force in outward direction, that means force acting on the ring is in outward direction, the tension in the ring will increase. So that increase in the tension we need to find here. So next let us write a problem. A charge capital Q is distributed uniformly on a circular ring of radius r, capital R, and a point charge Q is placed at the center of the ring. Now we need to find the increase in tension in the ring due to that repulsive force. So a charge Q is distributed uniformly on that circular ring of radius r. If a point charge q is placed at the center, find increase in tension in the ring. And so now let us see how to solve this. So actually this type of problems we solved like in elasticity topic, a similar problem. A similar problem we solved in elasticity topic and we solved in surface tension topic. So just we take a small element of the ring and then we find that force between that element and this charge. So now I am taking this small element of the ring here. So let us take this small element of the ring, very small element of the ring. So I am drawing here. This is actually very small only. So just to identify that I am drawing like this. So this angle is theta, this angle is theta. Theta value is very small. That means like suppose we can cancel this element as like this. Very small element we need to cancel here actually. So that I am drawing some big diagram to understand the reason. So that theta value we are taking here. And now this force is there. That means this is the Q. And now here this force will be there here. The repulsive force acting on this element dF will be along this direction. And due to this some tension will be developed in this string in the ring like this. Tension will be developed in the ring. And so that now we can write this as so this is the element what we are taking. Is it clear? This is the element what we are taking. And now the forces acting on this element we are representing. There will be some tension which is along that string. So the tension will be there here T and T. And because of this charge there will be some repulsive force acting on this. So that repulsive force will be along the direction. And so now just in equilibrium we can balance that forces here. You can resolve this tension into components. If this angle is theta, then you can take this angle as theta. And so that this will be T cos theta you can write. And T sin theta will be in downward direction. And similarly this angle will be theta, and so that this angle you can write it as T cos theta, and downward direction T sin theta you get. So I am writing it as 2T sin theta. And so again we can say that this two T cos theta and T cos theta terms are cancelled, and then only we need to balance these two forces here, dF and 2T sin theta. As the system is in equilibrium, then they are we can say that they are equal. So I can write this as 2T sin theta is equal to dF. And so this value we can here we can mention it as theta is small, we are taking very small element. So sin theta can be approximately taken as theta. That is approximation. So I can write this as 2 into theta. Instead of this sin theta I am taking it as theta. This is equal to, now dF value, the force acting on the element. So the force acting on the element I can write as K into dQ into Q by R square we can write. That means Coulomb's law. Just we are applying the Coulomb's law between this and this element. This we are taking a small element, and then we can apply the Coulomb's law there, where dQ is a charge present on that element. So here again first I am writing that dQ value here. The dQ value we can define it as Q by 2 by R, because now that Q is distributed on the complete circle into that 2 theta we need to write here, because this total angle we are taking it as 2 theta. So 2 theta we into R d theta formula. So here we are taking this small element of this ring. So in this the force is acting on this element of like T tension in this ring and tension in this element. Now the repulsive force between this point charge and this element is dF is acting in upward direction. And so now we are resolving this T into components like T cos theta, and this is again T cos theta. Its vertical component will be T sin theta, and for this also T sin theta. So in equilibrium we are balancing these forces, like 2T sin theta is equal to dF. And we are taking as theta is small, then sin theta is equal to theta we are taking. So then 2T into theta is equal to K dQ into Q by R square, where dQ is defined like this. So then dQ value is total charge Q by total length 2 pi R into length of this element, that is nothing but 2 theta into R. So I can write this as q by pi into theta I can write. And so that this value we can mention it as, so let us substitute this dq value here, k into q by pi into q into theta by r square. Now we can do the simplifications here. So like here you can write this as this theta you can cancel on both sides. Therefore this k is equal to k into q by 2 pi r square I can write. And so then if we substitute this k value, which is our proportionality constant, so I can write this as k q, that means q into q by 8 pi epsilon naught 8 pi square epsilon naught r square we can write here. So this is the tension developed in that string because of this repulsive force. So see once again. So I am defining the first charge of this small element. We are taking a small element here such that it subtends a total angle of 2 theta, where theta is small we are taking. So then dq is the charge of this element we are defining here. dq is nothing but q by total charge per total length, our lambda value charge per unit length, into this length of this element. So observe here, length of this element means we can write it as this total angle 2 theta into r we can write. And so that this dq value we are writing this 2 r you can cancel here, so pi by theta and q by pi into theta you can write. Now we are taking this small element of the ring like this. Just here the tension in this string will be acting here, and next here we can balance these forces like df, repulsive force will be there, repulsive force between the charge present on this element and this point charge. That repulsive force will be df will be along this direction, and tension components will resolve here, then these two components will cancel with each other. Then 2t sin theta will be downward direction. So just we are taking this 2t sin theta is equal to df and theta is small. So we are replacing sin theta with the theta. Then you can simplify here. We are substituting just a dq value by using this equation. Then if you simplify that, then finally you get this tension expression here. So this is the tension acting in this string when the charge is placed at this center of the ring. Based on the continuous charge distribution, here I will give another problem. You solve the problem, and actually because such a problem we already solved in gravitation topic. Such a similar problem you can solve yourself. Like here we calculated in the beginning of this continuous charge distribution, we calculated like force between a rod and a point charge. Now I am taking two continuous objects, like both are rods I am taking here. So here charge q is distributed here on this rod, and here also the charge q is distributed on this rod. And length of this rod is suppose say L each, and the separation between those nearest ends is also L. So that means that let's go like this. Now we need to find the force between these two rods. That means force acting on one rod due to the other rod. Electrostatic force acting on one rod due to the other rod. So then we need to take the small elements. We solve the similar problem in gravitation. You can solve this problem in a similar way. So then next there are certain problems based on this Coulomb's law, and with generally some time period calculation problems are there. Those problems I will explain in the next class. So now we have to practice these problems, and almost you have to complete this worksheet based on the Coulomb's law here, because we discussed almost all the problems. Some time period calculation problems are there. Those problems I will explain in the next class. So you have to complete the problems based on the Coulomb's law in all levels. That means level 1, level 2, level 3 and level 4 and